provide strong force interaction, right? Strong nuclear force interaction. So, I mean, left to themselves, the protons would probably not want to be very close together because they're all like charges, they repel each other. But there's also neutrons in the mix of things, and protons and neutrons are both made up of quarks, which interact with each other through the strong nuclear force, and the gluon force carrier particle is literally gluing together protons and neutrons. And this is very important in the heavier elements especially as well, because remember, this is actually important for stars and how stars die, because if it becomes too difficult to keep making more and more stable nuclei, then you're actually going to stop doing nuclear reactions within stars. And that's actually how a star can run out of its nuclear power. Okay. So things like nuclear binding energy and things like that that we have talked about in the past are sort of at play with all this. Okay. So the protons crammed together in atomic nuclei all repel one another electromagnetically. The strong force acting among their constituent quarks thankfully overcomes this repulsion and tethers the protons tightly together. But a rather small change in the relative strengths of these two forces would easily disrupt the balance between them and would cause most atomic nuclei to disintegrate. Furthermore, were the mass of the electron a few times greater than it is, electrons and protons would tend to combine to form neutrons. So neutrons can actually also disintegrate. Depending on its energy, a neutron can actually disintegrate to make a proton and an electron and some, guess what, neutrinos. So, if the electron was a little bit bigger in mass, then electrons and protons would tend to combine to form neutrons, gobbling up the nuclei of hydrogen, the simplest element in the cosmos, with a nucleus containing a single proton, and again disrupting the production of more complex elements. So if electrons were a little bit heavier and made neutrons a lot with protons, then that could have really disrupted the formation of heavier elements. And guess what? We are made of heavier elements. We're made of things like carbon, oxygen, all that, which are the heavier elements. The Big Bang just gave us hydrogen and a little bit of helium and trace amounts of lithium. So if we don't make heavier elements in environments like stars and in the first stars and galaxies, we would not be here. So this is a very, very important thing to appreciate, which is that it's a good thing that electrons and protons didn't get together too much to make neutrons, which could have disrupted and not made the heavier elements. So once again, were the mass of the electron a few times, I guess it would have to be a few times greater than it is, electrons and protons would tend to combine to form neutrons, gobbling up the nuclei of hydrogen, the simplest element in the cosmos, with a nucleus containing a single proton, and again disrupting the production of more complex elements. Stars rely upon fusion between stable nuclei and would not form with such alterations to fundamental physics. The strength of the gravitational force also plays a formative role. The crushing density of matter in a star's central core powers its nuclear furnace and underlies the resulting blaze of starlight. If the strength of the gravitational force were increased, the stellar clump would bind more strongly, causing a significant increase in the rate of nuclear reactions. But just as a brilliant flare exhausts its fuel much faster than a slow-burning candle, an increase in the nuclear reaction rate would cause stars like the sun to burn out far more quickly. So we actually know that massive stars require more fuel, obviously, to stay burning, but that also means that they burn out more quickly. This is sort of similar to that. So the more massive stars die younger, die more quickly, and then same thing here. So an increase in the nuclear reaction rate, if the nuclear reaction rate was a lot more, then things like our sun would burn out faster. Okay, so that's not good either. This is all very finely balanced in nature. I hope you're appreciating is that everything is kind of super duper